In the old architecture of physics, what we now call classical or Newtonian mechanics, the universe appeared almost reassuringly simple, like a well-built clock whose gears never change their shape, no matter how fast they turn. In that worldview, mass was treated as something absolute, immutable, and indifferent to motion. Whether an object rested quietly on a table or raced through space at great speed, its mass remained the same. This idea formed the backbone of classical intuition, and for centuries it worked with astonishing success. To understand this, one must first enter the Newtonian imagination. Sir Isaac Newton described motion through a set of elegant laws where force, mass, and acceleration were intimately connected. The most famous of these relations is written as F may, here, force, F, is what causes change in motion. Mass, M, is the measure of an object's resistance to that change, and acceleration, A, is the resulting change in velocity. In this framework, mass is the stubbornness of matter. A heavier object simply resists motion more than a lighter one, but that resistance never changes with speed. A cannonball moving slowly or rapidly still has the same M. The equation does not allow mass to evolve with motion. It is fixed like a carved number in stone. This idea extends naturally into energy considerations. In classical mechanics, the kinetic energy of a moving object is expressed as E for K Chaos frac 1 2 me $2. This equation reinforces the same intuition. The energy increases with velocity, v, but mass, m, remains untouched. You can double the speed and the energy increases by a factor of 4, yet the mass remains a constant parameter describing the object itself. There is no hint here that motion could alter the very nature of mass. Instead, motion and substance are treated as separate domains, one dynamic, one fixed. This separation shaped centuries of physical thought. Engineers built bridges, astronomers mapped planets, and artillery experts calculated trajectories, all under the assumption that mass is invariant. A kilogram of iron on Earth is the same kilogram in the heavens. This was not just a mathematical convenience, it was a deep philosophical belief about the stability of nature. Even momentum, defined as PTR multiplied, follows the same structure. Mass multiplies velocity, but does not depend on it. In this picture, velocity is the only changing actor. Mass remains a silent constant behind the scenes. It is the stage upon which motion plays out, never itself part of the performance. However, this clarity carried a hidden limitation. It was constructed entirely from experiences at everyday speeds, walking humans, flying arrows, falling stones, and orbiting planets. In that domain, velocities are tiny compared to a universal benchmark we had not yet discovered, the speed of light. So long as motion remains slow compared to this cosmic limit, Newtonian mechanics appears flawless. Yet even within this seemingly perfect structure, there was a subtle philosophical tension. If mass is truly invariant, then why does nature behave so differently at extremes, such as in electromagnetic phenomena or the motion of light itself? Why does light not obey the same rules as a thrown stone? These questions quietly accumulated beneath the surface of classical physics, like pressure beneath still water. The crucial assumption that time and space are absolute was never questioned in Newton's framework. Time flows identically for all observers, and space is a rigid stage. Under this assumption, mass naturally appears constant because the geometry of measurement never changes. There is no room for motion to reshape the measuring rods of reality itself, but this is precisely where classical intuition begins to break when confronted with high-speed reality. As later experiments and theoretical insights revealed, space and time are not fixed backgrounds. They stretch, contract, and intertwine depending on motion. Once this realization enters, the idea of constant mass begins to lose its foundational support. Still, within Newton's universe, everything remains beautifully consistent. The equations F true ma are quad p mv are quad ek frac 1 2 mav 2 zor form a closed logical system where mass is always the same, regardless of how fast the object moves. It is only when we push nature toward extreme velocities, close to the speed of light, that this serene picture begins to dissolve, revealing that what we once called mass is not as absolute as it seemed, but part of a deeper interplay between energy, motion, and space-time itself. If classical physics treats mass as a fixed identity, then the relativistic view, born from the necessity of understanding motion at extreme speeds, forces us to reconsider what we even mean by mass. The idea of relativistic mass free emerges not as a simple correction, but as a conceptual bridge between intuition and the strange geometry of spacetime. To enter this idea, we must begin with the behavior of momentum at high velocities. In classical mechanics, momentum is written as p guys me swas, and this works beautifully when speeds are small. But nature refuses to remain classical when velocity approaches a universal limit. The speed of light, denoted as c r 299, 792, 458, text, ms stars. At such extreme speeds, experiments and theory converge on a modified form of momentum. Instead of the simple product, mv, momentum must be written as p r gamma m. Here, something profound appears, the factor on gamma, known as the Lorentz factor. It is defined as gamma dur frac v1 sqr tau v1 frac by 2 c2 while this single expression contains the entire mystery. As long as v is small compared to c, the term frac v2 c2 is nearly zero and gamma approx 1. In that limit, we recover Newton's world effortlessly, but as v grows closer to c, the denominator, the future skeet line ones, frac v2 c2 dollars shrinks dramatically, causing gamma to increase without bound. Now here is where the idea of relativistic mass naturally arises. If we rewrite momentum as p as mvg gamma halves, it becomes tempting, almost psychologically irresistible, to group terms differently and define an effective mass. Mem text relay chi and gamma m twelve, so that momentum looks formally identical to the Newtonian expression p prim I text real I eve thus. This is the heart of the relativistic mass concept. It suggests that as velocity increases, the mass of the object appears to increase according to a text real soon fragment escrit 1 and frac 5 2 2. From this perspective, mass is no longer constant. Instead, it becomes a function of velocity. The faster an object moves, the larger its relativistic mass becomes. This interpretation was historically useful because it preserved a familiar structure. Newton's equation, P times mv, physicists could continue thinking in classical terms while quietly embedding relativistic corrections into the mass term. In this picture, mass behaves like a fluid quantity, growing as motion becomes extreme. To understand why this happens, consider what force must do in relativity. Force is defined more carefully as the rate of change of momentum. F doors nafrac dp ditois substituting relativistic momentum, we get F by nafrac di gamma mv. Now the situation becomes fundamentally different from classical mechanics because our gamma depends on velocity and velocity depends on time. Force is no longer simply proportional to acceleration. Instead, force must account for the changing geometry of space-time itself. As velocity approaches the speed of light, gamma grows extremely large. This means that even a tiny increase in velocity requires an enormous amount of force. If we interpret this through the lens of relativistic mass, we say the object's mass is increasing, making it harder to accelerate. This leads to a striking physical interpretation. Motion itself resists further motion. The closer an object gets to the speed of light, the more massive it appears dynamically, as if nature is imposing a resistance barrier. We can also connect this to energy. The total relativistic energy is given by E jar gamma MC2 jar. Expanding this idea reveals E MC2 pla and gamma 1 MC2 jar. The first term MC2 represents the rest energy, and intrinsic energy even when the object is not moving. The second term represents kinetic energy in relativistic form. As velocity increases and gamma increases, and so energy increases dramatically. If we again adopt the relativistic mass viewpoint, we could rewrite energy as E m a text rel c $2. This makes the analogy even stronger. Energy and mass appear interchangeable in a dynamic sense, with motion inflating mass-like behavior. Thus, relativistic mass is not a new kind of matter. It is a way of describing how energy contributes to inertia. The deeper truth is that inertia itself is not fixed, but emerges from the geometry of space-time encoded in gamma. And yet one must be careful. The modern view of physics prefers to avoid the idea that mass itself changes. Instead, it keeps mass invariant and attributes all changes to energy and momentum. But historically, the concept of relativistic mass served as an important stepping stone, a way for the human mind to grasp an unfamiliar reality using familiar language. In essence, key point 2 reveals a subtle psychological transition in physics, from thinking of mass as a static property to recognizing that what we call mass increase with speed is really the visible shadow of a deeper structure governed by gamma Einstein frac van 1 as Q1 and frac var 2 Q, a single factor that quietly governs how reality resists being pushed toward the speed of light. If the idea of relativistic mass once served as a bridge for human intuition, then the deeper maturity of modern physics lies in realizing that the bridge was never the territory itself. The real structure of nature is more subtle. Mass does not increase with speed. Instead, what increases is energy and momentum, while the rest mass remains an invariant feature of the object, like its identity written into the geometry of spacetime. To understand this shift, we must return to what relativity truly preserves. At the heart of special relativity lies a constant that never changes for any observer moving at constant velocity, the rest mass, often written as m. This is the mass measured in the object's own rest frame, where its velocity is zero. In that frame, energy is not complicated. It is simply an E $0 by m2. This equation, perhaps the most famous in physics, is not about motion. It is about existence itself. Even when an object is completely at rest, it contains an intrinsic energy proportional to its mass. This is called rest energy. Now, when the object begins to move, something more intricate happens, not to its mass, but to how energy and momentum are observed from different frames. The total energy of a moving object is given by E gamma m squared hours, where the Lorentz factor is gamma density frac v1 s by 1 on frac by 2 c2. This equation does not say that mass has changed. It says that energy depends on motion in a way that grows rapidly as velocity approaches the speed of light. To see why mass remains unchanged, we must introduce the most important invariant relationship in special relativity. Energy, momentum, and mass are tied together by E so darn equals PC plus MC times 2 dollars. This equation is not just a formula, it is a geometric statement about space-time. It tells us that energy is not independent of momentum, and neither is independent of mass. They are three projections of the same underlying structure. Let us carefully examine each component. The momentum in relativity is P I gamma mv. The energy is E n gamma m 2. Now notice something crucial. Both depend on gamma, both depend on velocity, but our mass m remains untouched. It is not multiplied by gamma in any fundamental law. It sits quietly as the invariant anchor of the equation. If we rearrange the energy-momentum relation E2 PC2 of MC2 $2, we see that the right-hand side depends only on m, not on velocity. This is why mass is called invariant mass or rest mass. No matter how fast the object moves, this quantity remains the same in all reference frames. Now, where does the illusion of increasing mass come from? It comes from trying to force relativistic physics into Newtonian language. If one insists on preserving the classical form, P stretch through me, then one is tempted to redefine mass as a text F size 3 frac P substituting relativistic momentum text F psi frac gamma m psi, we obtain text F gamma m psi. This is the origin of relativistic mass. But notice what has happened. We have not discovered a new physical property. We have merely absorbed the Lorentz factor into a familiar Newtonian structure. It is a linguistic transformation, not a physical one. The deeper truth is that force is not simply F ma in relativity. Instead, it must be written as F ra frac dpt, since P gamma mv, force becomes F frac dt in gamma mvt. This expression shows that acceleration is not linearly related to force anymore. The resistance to acceleration comes not from an increase in mass, but from the geometry encoded in gamma. Energy also clarifies the misunderstanding. The kinetic energy of a relativistic particle is dk gamma 1 by 2 dol. This equation shows that the extra energy gained from motion depends entirely on gamma, not on changing mass. The rest mass, m, remains constant. What changes is how much energy is required to continue accelerating the object. Thus, instead of saying mass increases with speed, modern physics says something more precise and more profound. The energy required to accelerate an object increases without bound as its velocity approaches, c, while its rest mass remains constant. This interpretation preserves the structure of relativity without confusing identity, mass, with dynamical effects, energy, and momentum. One can think of it this way. Mass is not a quantity that stretches or grows. It is a label attached to the invariant core of an object's existence. Energy, on the other hand, is what changes depending on how that object moves through space-time. Momentum is how that energy is directed. In this sense, relativistic physics does not make mass larger. It reveals that motion does not belong to mass at all. It belongs to space-time geometry. So the final clarity is this. When we say mass increases with speed, we are describing an old language struggling to express a deeper truth. The modern formulation is cleaner, sharper, and more beautiful. Mass, invariant. Energy, frame-dependent. Momentum, frame-dependent, bound together forever by E2 PC2 plus MC2 dial, a single equation that quietly replaces the illusion of changing mass with the reality of changing space-time structure. If there is one idea that forces the human mind to confront its own limits, it is the existence of a cosmic boundary that no object with mass can ever cross. This boundary is not a wall in space, but a limit woven into the very structure of space-time itself, the chance speed of light, denoted as c. And it is here that the concept of relativistic mass increase finds its most dramatic consequence, not as a change in matter, but as an infinite demand for energy. To begin, let us recall the Lorentz factor, the silent governor of all relativistic motion. Gamma, or frac 1, I squat 1, and frac by 2, by 2 does. This single expression controls how the universe behaves as velocity, v, approaches the speed of light, c, at everyday speeds, where v RLLC, the fraction, on frac graph 2, c2 is nearly zero, and thus the gamma haprox $1, but as v increases toward c, something extraordinary happens. The denominator, Asher squat 1 and 1, and frac 5 2, c2 shrinks towards zero, and as any mathematician knows, division by an ever smaller number produces a rapidly growing result. Thus, ein gamma change to hinfty r quad r text as r quad by r2 color. Now let us connect this to energy. The total energy of a particle moving with velocity by v is e the gamma mech 2 dollar. Substituting the behavior of and gamma, we see that as velocity approaches the speed of light, e and to infinity. Now, this is the first and most important consequence of the speed of light limit. the energy required to reach C becomes infinite. If we express kinetic energy more explicitly, we write E shakai chu gamma 1 fems to dal as V into C. This becomes EK into Himpty Siam. No matter how powerful the engine, no matter how advanced the civilization, no finite energy source can achieve this requirement. This is not a technological limitation, it is a structural property of the universe. Now, earlier interpretations of relativistic mass help us visualize this in classical terms. If we define I text real eins gamma m, then momentum becomes pu eins m r text real I darn as v r to c. Since gamma into empty, we find m I text rl into empty prime. This gives the intuitive picture. The object becomes infinitely massive and therefore impossible to accelerate further. But as we now understand, this is only a reinterpretation of energy growth, not a literal increase in intrinsic mass. The deeper truth lies in the force required to change motion. In relativity, force is defined as F by frac dp to t pi with momentum p chi nigama me twice. We see that force depends not only on velocity, but also on how spacetime itself resists changes in motion. As velocity increases, the derivative of n gamma with respect to time becomes significant, meaning that each additional increment in speed requires more force than the last. This leads to a remarkable physical behavior. Acceleration diminishes as velocity increases, even under constant force. Unlike Newtonian physics, where constant force produces constant acceleration, relativity introduces a saturation effect. Now consider the ultimate limit. If an object with mass m0 were to reach v equals c, we would have gamma very nefrac 1 as quart place 1 nefrac c2 c2 very nefrac 1 this which is undefined and mathematically diverges to infinity. This is not merely a calculation, it is a statement about reality. No inertial frame allows a massive object to reach the speed of light. To understand why, we can examine the energy-momentum relation, E2 PC2 plus MC2 2 tau. For a particle approaching light speed, momentum becomes extremely large, P the gamma mv into infinity, so the equation becomes dominated by E2 tau naprox, PC 2 tau. This means energy and momentum grow without bound while mass remains fixed. The structure of space-time itself enforces this divergence. Photons, however, behave differently. For light, rest mass is 0, m sharp 0 dal, so the equation reduces to E down p stars, and light always travels at speed, c, never requiring acceleration from rest. This is why photons do not experience the infinite energy barrier, because they do not possess rest mass. For objects with mass, however, the situation is fundamentally different. The closer they approach, c, the more energy is required to squeeze further motion out of them. It is as if space-time becomes increasingly rigid in the direction of motion, resisting any attempt to exceed its built-in limit. This leads to a profound interpretation. The speed of light is not simply a property of light, it is a property of space-time itself. It defines how fast cause and effect can propagate, how quickly information can travel, and how motion is geometrically structured. Thus, the so-called mass increase with speed is actually the visible symptom of a deeper truth. The universe imposes an infinite energetic cost on reaching its ultimate speed limit. And so we arrive at the final realization. The equation Husson gamma I trying frac 1 chi is cut I1 I frac v2 $2 is not just a mathematical expression, it is a boundary condition written into reality. It tells us that motion has limits, not because objects become heavier in a classical sense, but because space-time itself refuses to allow infinite acceleration within finite energy. The speed of light is therefore not merely a number, it is a declaration from the universe that infinity has no place in finite motion.